Cool, I'll move on. Okay, for part B, we have a circuit with a load here and a voltage source. We've been given that the power, so first we're identifying everything we've been given, is 400 watts. And we have a power factor of 0.766 slightly. So for the first part, it's finding the total current in this circuit. To do that, we can use the power and the power factor. So if you remember our formula for the average power, that is half voltage maximum, current maximum times the power factor. And that should be clear from your work in labs and lectures. So does anybody know what the voltage maximum would be just from this? Yep, just 100 volts, because we're using both these elements as the load, not just Z here, which might be a bit confusing, but yes. So rearranging equals 400 watts. We can get the I maximum equals, that would be 800 V max times power factor equals 10.44. And then next step is to find the angle of the current, because we need both of those for the complete description. I think we know that from the previous question, the power factor is related to the angle through cos of the angle here. So we know that theta equals cos inverse of 0.766, which equals 40 degrees. Does anybody know if this is positive or negative 40 degrees? That's an important thing to note. So looking back at the question, we have a lagging power factor. So what does that say about the angle? Negative is for a leading power factor. So if we look at the power triangle, I'll draw that up really quickly. We can see that this is for a positive theta and a positive reactive power, and that is for a net inductive load. And so that will be a lagging power factor. And with a negative angle, we get a net capacitive load. And that will be a negative theta. So since we have a positive lagging power factor, we have a positive phase angle here. So that's something to make sure you don't trip up on. And simply combining both of those, we get I equals 10.44 angle. Oh, sorry, I skipped a step. From theta, we know that the voltage minus the current equals 40. Using the phase of the voltage source, we have 30 degrees. And so rearranging, I equals negative 10 degrees. I 10.44 angle negative 10 degrees. And that is an answer. Is everybody happy with that so far? Yep. Great. So next we have the power triangle. I've started sketching a couple of those. It asks us for the average power, the reactive power, and any relevant angles, as well as the apparent power. So we know that we have a lagging power factor, so our power triangle will have a positive angle. And we can use the value previously calculated, 40 degrees. Does anybody know what the average power will be? It's pretty simple. It was the 400 watts that they gave us in the question. In terms of finding the apparent power, or the magnitude of the apparent power, there's a shortcut that you can take, and that is that the apparent power equals to the average power divided by the power factor. And that gives us 400.766 is 522 volt amperes. It's important to remember those units, it's not in watts. So that's S. And then Q, using simple trigonometry, we have Q equals magnitude of S sine of R theta. And that is 336 volt amperes reactive. And that is a complete description of our power triangle. Yep. Okay, and now it wants us to find the value of impedance Z. We know that the total impedance of our entire load will be the voltage divided by the current from Ohm's law. So we can use known voltages and currents that we previously calculated to say that Z total is equal to 130 on 10.44 angle -10. And we know that when we're dividing, the phases subtract. So that is equal to 9.58 angle 40 degrees. That is ohms. Getting from our total impedance is simply subtracting the 4 ohms we see in this load to leave us with just Z. So we will take Z equals Z total minus 4. And again, you can split this into the real and imaginary parts, or you can use a complex calculator and you should get 7 angle 54 degrees in ohms. And I think that covers that question. Does anybody have any problems? Great, I'll move on. For question 2, we are asked to find the Fourier series of this periodic signal. So the first thing to note is that it is indeed periodic, so we can apply a Fourier series. Other things we might want to notice is if there's any DC offset. Is there a DC offset in this scenario? Yeah, -1 volt. Another thing that's helpful to note is whether this is an even or an odd signal. Does anybody have an idea? Yeah, it would be an odd signal. So if we flip it over the y-axis and negate it, we can see that we get the same signal, assuming we remove the DC offset. The reason we identify those two things is it gives us a shortcut in finding the coefficients. We know that since it is an odd function, there will be no coefficient for the cosines because those are even functions. So we can automatically assume that an is always equal to 0. Feel free to do the, yes. So we can do that by observation. And so we can see that we could get this signal centered around, it's from 0 to -2. So it'd be centered around -1. And so we can, by observation, say that there's -1 offset. So if you want, you could just say that A0 is -1 from that, but we will use the formula to derive that, as well as B and coefficients. So starting off, let's identify the period. We can see that the period repeats from here to here. And that is a T of 2. From that, we can get the frequency. And that is 2 pi on T. And then 2's cancel, just pi radians per second. Okay, and I'll just quickly go over the formula. So we have A naught is equal to 1 of the period integral from 0 to period ft dt. So the next thing we need to do is find out what f of t is. And we're only looking at one period, so we can just look at this section here. We can see that it's linear, so it'll be of the form of ax plus b in terms of t in this scenario. We can see that the gradient is 1 because over a distance of 2, it rises 2. Explanatory. And we can see that when t is 0, we get -2, so that's -2. And then integrating that, subbing in the values of t, we get a0 equals r 0 to 2, 2t equals 2 dwt. I hope everybody's following what I'm doing here. Just integration. Okay, yep. So that's going from here. We're using, oh, sorry, the gradient is 1. I think I mentioned that earlier. I wrote that. We have a rise of 2 and a run of 2, so the gradient is 1. Thank you for calling me out on that. Yep, so that's 2 months. And we get the expected answer of 1, or -1. That's what we expect the DC offset to be. Next, we're going to need these two formulas that they give us. So I'll zoom in on them so you can get a good look. So when we find A of n, we get this formula 2 on t f t sine m dt. So simply subbing in our values, we get 0 to 2. Sorry, yes, I am doing Bn. And we already determined that an is 0 because it is an even function. So we can quickly cut out that work for us. Okay, next step, simplifying this out, we have what we will notice is the equation they gave us earlier, plus another integral, which is just a simple sinusoid. So this is as simple as taking exactly what they have here and applying it to our specific equation. So x of sine ax equals 1 on a of 2 sine ax minus x on a cos ax. So simply applying that, we have, try and get it so you can see the formula as I'm going. So we have 1 on n omega squared because n of omega is a in that formula, minus Rx, which is t, on n omega plus. And then for this one, it's just normal integration. So we have positive. It's the integral of 0 to 2 because we are integrating over the entire, period here from 0 to 2. Yeah. Okay, I'm going to do some simplification where I just look at b of 1 because it asks us for the fundamental frequency only. So we don't have to worry about n. And that is equal to omega. It's just pi. So sine of 2 pi, something in that, is equal to 0. Have I done something wrong here? In the which term? The 1 on n squared. Yep, that comes from this formula here they've given us. Yeah, and so we're just simply applying that. So sine of 2 pi should be 0. I've done something wrong here. Can anybody spot it?
Like 2 pi 0. Zero.
For which one?
The 2 on pi of 0. Like
Just
it's
here.
T is 0, right? So it shouldn't be 0.
Yes, that is where it is. Thank you. So yeah, subbing in 0 there instead of 2. Here. That -2. Okay. That is B of n, and then we simply put those together. We just use B of 1 because we're just doing the fundamental. So f of t is equal to a0 plus, and we'll ignore the sum because we're just doing B1 sine of, and that is I guess we can sub pi t there if we wanted as well. Great. Did anybody have questions with this working? No. Okay. And yep, that's it for just A. Do note that in an exam, you should specify that, write it here as well. Zero. Just so the markers know what you've done. Yes, this question gives you this formula we needed to use just here. No, you don't need to know this formula, but anything they give in the question, you assume that you're going to have to use. You will have the normal formula sheets for your Fourier transforms and all of that. Yes, it's recorded. Okay, for the next question, we have, yes. What was that? Yep, I've just set it up here. We can assume that an is going to be 0 because we have an odd function. Over here, we can see that if we were to mirror this function on the x-axis, we'd get something like this. Oh, I guess we'd zero it as well. And then negate this, we get color. This signal, which is the same as our original signal. So we know that it's an odd function. And since the cosines are an even function, we know that there will be no cosines present in the Fourier series. Does that make sense? Yeah, so that's just a shortcut that you can apply in the midterm to save you time. Okay, for question B, we have a Fourier transform question. So that's where you will want to be using your formula sheet or have it memorized. In this case, we have an f of t that is not a periodic function. So we're going to have to break it down into different pieces. So solving B. Yes. We can split f of j. And then this is just the formula for the Fourier transform. We know that we can split f of t into two signals. We can do -1 from -1 to 3. And then we can also have another -1 from 1 to 2. And by the law of superposition, that will add to give our signal that we have here. So writing that here, -1 plus 3. The reason I split it up this way is you can see we've got two integrals that are basically the same function. You could go from -1 to 1, 1 to 2, and then 2 to 3, but this makes it a lot easier. And then we just apply the same integration steps. Is everybody comfortable with that Fourier transform method? How did I decide these limits? We can see that outside of these limits, we have 0. So we can just do limit the Fourier transform to where we have our signal. Okay, yeah. As I said, you could do it that way. So you could go one integral from -1 to 1, and you could do another from 1 to 2, and then from 2 to 3. But we can also know from superposition that if we do two signals, one from -1 to 3, and then one from 1 to 2, and add them, that they get the same result. And so that's just a lot easier to calculate. So yeah, that's why I recommend taking a look at the question before you just start going into calculations. Think about how you might most efficiently solve the problem. And yes, obviously, anything outside of -1 and 3, it'll just be integrating over 0, so you get nothing. Great. The next property builds into this, and that is using the time shifting property. Is everybody familiar with what the time shifting property is? Yep. I'll write that down just in case. So let's see, f of t minus a is equal to e to the -j, I get a f e to the -j. So just multiplying it by that exponential, we have a time shift. So that makes this problem really easy. We just take our original f of j omega and multiply it by this exponential. So I guess we could say and in this case, a value is -2, because we're shifting by a +1 over here. And then we know from exponential rules that we just add the angles using Euler's form. We get j omega equals sorry, we have -j2 omega up here. Sorry. This is a +2 because we're taking a negative of our a equals -2. So up here, this is just an e to the 2j omega. Sorry for that mistake. So okay, and that's just our time shifted Fourier transform. Is everybody okay with that? Any questions? Show the question again. Yeah, I'll move on to the next question. So for question 3a, we have an RLC circuit. They want us to prove that the response of the transfer function is as shown. So again, we should take some time to look at our circuit and decide what the easiest way to solve this would be. To me, it looks like if we add these two components in parallel, we can simply use voltage division to get V0 in terms of VI. That will be our transfer function. So similar to the first question, we are finding the impedances of capacitance and inductor. So we can start with ZC. Then if we parallel, we get ZC times ZL. So that is j omega L on j omega C. And then divided by the addition. Then we can simplify this down to get a nicer equation to work with by multiplying both sides by j omega C. So we just get actually, no, we'll just times everything by sorry, let me just L on C. Yeah, okay, I will times by j omega C. So multiplying j times j is -1 omega squared LC. And I think everything else comes out quite clearly. And then in terms of our transfer function, we have h of j omega is voltage division. It's always important that we show the markers what techniques we've been using. Yep. Okay, yeah, I'll explain it in more detail. So we're multiplying by j omega C in the bottom, and that moves this term up here. So we just get j omega L. This is 1, j times j is -1, the omega is squared LC. And that should come out. First step, deriving 1 on j omega C and j omega L. Yep, that's just our formulas for impedance, capacitance, and inductors. Yep. And this step is, I should clarify that h of j omega equals and then we can use voltage division. So we have our parallel combination that we worked out here is there, and then we have the resistance and then adding the parallel combination in the bottom. That's voltage division. We can again simplify this by multiplying this out, through top and bottom, and that gives us j omega L on Cool, so that is our finished transfer function. It's asking us to prove that the magnitude of the transfer function is equal to this value. So we will take the magnitude here. In order to take the magnitude of something, we can split it into the numerator and denominator and do those separately. It is the square root of the real part squared plus the imaginary part squared. So simply on the top, you only have an imaginary part. And so omega L squared square root would just be omega L. And then on the bottom, we have square root minus omega squared RLC, which is our real part squared, plus our imaginary part omega L squared. Does that match what they wanted? Oh, okay, they've done it in terms of RC in the top. Okay, so we'll divide everything by RLC to get their solution. And then so if we divide by RLC here, it's dividing by RLC squared. And that is in the form they wanted in the question. Is anybody confused about how either we found the magnitude or the transfer function? No, good. And that's it for A. For B, we're using part A to make a sketch of the amplitude spectrum, and it asks us to label all important features given these values. So we can simply sub those in. So I guess I have the final value here, and it's actually equal to 1. I'm sure you can all sub that in your calculators to confirm that. But using these values, we do have the magnitude equal to 1. So that is our resistor equals 159.15 ohms, inductance 202.64 microhenries, and capacitance 5 microfarads. An important thing to note is our Fourier series is just a cosine waveform with an omega A here specified as 31,416 radians per second. So we can just use that omega A to sub into omega in our magnitude here. And that should give us 1 at the output. So now that we know what the magnitude is for these specific values, we can use that to find V0. So we know that magnitude of H of J omega is equal to the magnitude of V0. And rearranging. So we know H of J omega is 1. And from this equation here, we can see that VI is 2 cos WA of T. We can see that the magnitude here is 2, just from inspection. That's 1 times 2 equals 2. Okay, does anybody have an idea of how we would turn this? We've got this one single magnitude value at, I'll specify that it's at omega A. Does anybody know how we would turn that into a magnitude spectrum? So if we remember the Fourier series of just a single sinusoid, it is just one Dirac delta function. It is just one single infinitely thin peak. And we can see that since our input is only a sinusoid, we have a magnitude spectrum, which will look something similar to just one peak. And that's what we see here as well. We've got a magnitude of just 2 at omega A. So we can simply write omega A and 2 magnitude of. Is anybody unsure as of why we can simply write this as our magnitude spectrum? Omega A is specified here as the frequency of our input sinusoid. So we only have one frequency component and it's a sinusoid, so we expect to see only one peak in our magnitude response, which is what we get. Yeah, important features is just omega A, we can say the value in rads, but we don't need to, and the magnitude is 2. Again, the hardest part of this problem is just knowing what to do, and knowing what a magnitude spectrum is made up of, and identifying that this is just one term in a Fourier series. Great, I'll move on to C. It's asking us about what happens when we use the same magnitude response, but increase the frequency slightly to 31,500 radians per second. It wants us to do this analysis without performing any magnitude response calculations like we did in the previous one. So we need to figure out a conceptual or qualitative way of understanding what will happen to our magnitude response if we increase the frequency. It says explain whether you expect the amplitude of the output voltage V0 to be larger or smaller than the value from part B and why. Does anybody have a start of an idea on where you might begin with this problem? Yeah, you can use voltage resonance. So to make this easy on ourselves, looking back at this circuit, this isn't a series resonant or parallel resonance yet, but using source transformation, we can turn it into a parallel resonance circuit and easily use those formulas. So I'll do that now.
Sorry, I didn't quite catch that. Could you please say that again?
Thank you, Siri.
No problem.
So, yep. Yep, so we just have a simple parallel resonance circuit, and we know you can find that in your lecture notes or the formula sheets that our resonant frequency will be 1 on root LC. So if we substitute in our previous values, what's that? Up here we have 202.64 microhenries and 5 microfarads. That gives us it gives us 31416 radians per second. which you will notice is the same frequency as given omega A up here. So that tells us that our circuit will look something like this. The peak is at omega A. That is because of the resonance of our circuit. And qualitatively, we could say that since omega A is the peak, any increase or decrease in frequency will result in a lower output magnitude. Yes. Yes, the one I just subbed in these values, you can do that in a calculator and you'll just get that it all equals 1. Problem? Yes, so you'll need to write out an explanation explaining resonance. So you could explain that as you increase omega to something they said 31,500 radians per second. So we'll say that this is our omega 2. We can see that it'll be somewhere slightly smaller than our resonant frequency, which we determined was omega A. So you can say that since we've determined that omega A is the resonant frequency, any change in frequency will result in a smaller magnitude. Okay. Online students, no questions? I'll move on to D. So have you covered mutual inductance yet in lectures?
Yeah, we might
Touch on it just this week? Yeah, okay. So this question involves mutual inductance. It's not a transformer question. I'm not sure. Have you done transformer questions? No. Okay, that's fine. I'll just cover this mutual inductance question, which should be fresh in your minds then. I'll start by briefly talking about the dot convention and how we use it and how I like to use it in analysis. So in the dot convention, we know that for a current going into the dot, we can treat the, if the current is going into the dot on one side, then we know that on the other side, the positive voltage will be at the dot. So for I1 going into the dotted side here, we can know that positive will be there and negative will be down there. If it's the other way around, I like to use negative I1 and say that there will be still positive here and negative here, but that's in terms of negative I1 if I1 was going in the opposite direction. So I like to always find the current that is going into the dot and just make that positive or negative depending on what they've specified. Okay, so to analyze in mutual inductance circuits, it's always easier, in my opinion, to use mesh analysis. We're dealing with currents. And in this case, we have two meshes. Let's I1 and I2. And those are the directions. We also have reactive components, and we're going to need to find the impedances of those. So let's call this ZC, J, omega, and omega is from up here. Oh, I guess I should start by finding what omega is. So F equals 1,000 hertz. Oh, yes, sorry. You're absolutely correct. Omega would be 1000 radians per second. And we know that we have a phase angle of 60. So B for angle 60 degrees. Now we can move on to our Z capacitor. That is negative J50. And then we'll call this inductor 1 and inductor 2. Sorry if this circuit is too small. I might draw a second one. And that is our resistor in combination with the capacitor using this impedance here. And then we have first inductance, which is J20. J40 ohms. Doing this. And our mutual inductance, which is already given for us, J17. Okay, so using KVL, so write KVL in our mesh analysis. On the first mesh, we have 4 angle 60 on the left-hand side. We have I1 times our impedance over here. And then we add, since the current is flowing through this inductor, and then we have to remember to include our mutual inductance. So in this case, I2 is flowing out of our dot, but I always like to think of the current flowing into our dot, so I will treat negative I2 as flowing into the dot in this case. So we will see a voltage across these terminals of negative I2 times our mutual inductance, which is J17. So we will add negative I2 times J17. Is everybody clear with why I'm doing this with the dot rule, the dot convention? I have online students saying, where would I find the recording for this?
I'll post it on the Teams channel.
The recording for this meeting will be posted on the Teams channel. And where are the answers for past midterms? I'm not sure if students are provided with all of the past midterms and answers. They would be on Moodle if you have a selection, but it will just be what you can find. I also believe Elsoc has some on their website. Yeah, so Moodle might, and I think Elsoc has a few. Yep, so we are using the dot convention to say that this I2, since it is flowing out of the dot, or as I like to think, negative I2 is flowing into the dot, produces a positive voltage at the dot and negative on the other end of the component. And then we use the current flowing into this component multiplied by the mutual inductance to get the voltage seen across the original inductor. Yeah, so that's how I like to use the dot rule. It's, you don't have to worry about different versions. It's always the same. It's always current flowing into the dot. Yep, so that is our first equation. We might want to simplify it up a bit. So yep, and then our second KVL equation, KVL2. We're looking at the second mesh over here. In this one, we will start with, I guess, 0 on the left-hand side because we don't have a voltage source. And then that is equal to starting with this inductor, I2, and I guess we can include this resistor as well, 10 plus J40. So going in this direction of current, we'll have positive here and negative here, the inductor, positive here, negative here for the resistor. And then we also have to include the mutual inductance. And again, we look at the current flowing into the dotted terminal and we see that is I1. And then we treat I1 as creating a voltage positive at the dot and negative at the other end. And so factoring that in, we get negative in our KVL equation, negative I1 times our mutual inductance, which is J17. Is that clear how I'm using the dot rule again in this scenario? Yeah, that's an important thing for exam, is always make sure that you're getting the right directions of voltage in these scenarios. So it's a positive current into the dot, creates a positive voltage across the component from the dot to the other end. And then for the simultaneous solution, we can set I1 equals to something to 1. Okay, and then this simplifies down to the check. Minus J100, I2 minus J17, I2. Again, 100 minus J117, I2. 60 solving for I2 gives us again here we've got two different forms, so we could use our formula or a complex calculator, whichever you're most comfortable using. That is then 100 minus J17. this is in milliamps. So you can do that calculation to double check for me if you'd like. But yes, I recommend getting a complex calculator to make these calculations quick and easy. Then we can sub that back in for our expression for I1. That is always include your units. Okay, so that is our currents in our mesh analysis. To ask us to do from there. Just finding the phasor currents. Cool. So is everybody clear with what I've done here and all the steps? Cool, okay. We're moving on to question 4. So here we have a simple integral to evaluate. The key thing about this question is you need to know about your Dirac delta function. So is everybody clear on what the Dirac delta is? You didn't watch the lecture? So our Dirac delta function is a function that exists at 0. So we have, and this is in frequency or time, but it's a function that has infinite magnitude and 0 width. So it's a single point. So I'll draw this in different color. We often normalize the Dirac delta to just be a magnitude of 1. And that would be a Dirac delta. So if there's no offset, so omega, we just have a single point at omega equals 0 with a magnitude of 1. Is this new to all of you? No? Okay. Very fresh, good. There's a few properties that come with the Dirac delta function, and I think you probably will have them on your formula sheet or in your lecture notes. For this equation, there's one property to remember, which is the integral between f of t Dirac delta of t minus a t is equal to f of a. And this is just a formula you're going to have to remember, and it can be easily applied, as you can see here, where a equals -1, and our f of t is e to the j10 omega. So we can see just from this that our integral So it's a simple question, but it requires knowing the formula and understanding what the Dirac delta function is. Is anybody wanting further clarification on this one? Yeah, it should be quite simple, just applying the formula. For this next one, we have what we can see is an exponential signal, but also a unit step function. So the first step will be identifying what the equation is for f of t. And again, we're just doing a Fourier transform question. So f of t is 2t times u of t, and u of t is our step function. So that's 0 up until 0, t equals 0, and then 1 everywhere else. You could use just the Fourier transform pairs, and this is a simple case on the Fourier transform table, and come up with an integral, a Fourier transform quickly, but I will go through the integration method to show you how it's worked out. All right, so we apply a formula. I'll write it here again just to remind you. Is our basic formula, and then we sub in our f of t. And also noting that our bounds, it's 0 for negative t. So we can say from 0 to infinity to e to the negative 2t e to the negative j of negative t. And we're ignoring the step function because we've included it in our bounds. So we can say it's going from 0 to infinity instead of negative infinity to infinity.
Explain why we use the step function. Yeah.
So we're using the step function because a normal exponential, so if we draw the plot for 2e to negative 2 negative t, sorry, it will look something like this. Approaching infinity as t goes to negative infinity, and approaching 0 as t goes to positive infinity. From here, we can see that every value for t is less than 0 is 0, and that's where the step function comes in. Step function is 0 for everything t is less than 0, and 1 for everything t is greater than 0. And so that's u of t. Sorry, I should have made that clearer. And so we can see multiplying these two functions gives us the graph that they plotted here. Okay, and then this is just a matter of solving the integral. Well, first I'll simplify it. We have two exponentials. Okay, and then on these bounds, we can see that as the exponential of negative infinity will be 0. So that equals 0, and then the exponential of 0 will be 1. So that's 0 plus 2 of j plus 2. And this is what you will see in the formula sheet. You will see that f of t of an exponential. So I'll write that here. You can see that matches our solution here. So where a equals 2, we can just sub in and get the exact solution quite quickly. Does anybody have any questions for that Fourier transform?
It's like in general, do we get a formula sheet in the exam? Like even the midterm?
When I did this course, it was online, fully open book, so we had access to all our notes. Double check. Usually you should have access to Fourier transform, Laplace transform formula sheets. You definitely will for the final, I'm pretty sure. But for a question as simple as this, I think it's best to go through the full working because I think that's what they're looking for. Okay, we have another Fourier transform question. This one has multiple different methods. You can directly apply the Fourier transform for the cosine or the sine. I'm not sure if you've encountered that so far. So at the moment, they've just given you this formula for an exponential converting to the Dirac delta function, which we just talked about in the frequency domain. So the first step would be to see how could we apply this formula to f of t. We know that they are giving us this formula, so we know that we likely want to use it to solve our question. So that leads us to see that cos and sine can be expressed in Euler's form in terms of these exponentials. So if we write out our f of t that way, we get t equals 3 on 2 e to the j t plus e to the negative j 50t minus 2 j2 e to the j 150t minus e to the negative j 150t. Is everybody familiar with these Euler's formulas for the cosine and sine? Yep, I'll take that as a yes. We can expand this and simplify, but I think it's pretty easy to see that this formula applies for each of these components of the f of t, and we can separate it and do each of the Fourier transforms separately. So e to the j omega t goes to 2 pi, the Dirac delta over omega minus omega naught. So for this case, our omega naught is 50. And yes, that's it. So we would get f of j omega. Directly applying this is 3 on 2. Sorry, we have to include the 2 pi. So that would be 3 pi, as the 2's cancel out, times the Dirac of omega minus 50 plus Dirac of omega plus 50. That should be clear from that formula. We can apply the same thing. We have plus, and then those 2's cancel out, and we have, I'm doing a plus here because j on the bottom, we can take the reciprocal and it becomes a negative j. And that is just plus j 2 pi Dirac of omega minus 150 minus the Dirac of omega plus 150. And then we've got a completed Fourier transform. So that's part I. Is everybody comfortable using that formula that they provided to find the Fourier transform? You can see that since we're just using addition and subtraction here, we can do it piecewise and apply the separate transform to each component. The next question wants us to sketch the amplitude spectrum. Oops. Sorry about that. Okay, yes. The next question is about sketching the amplitude and phase spectrums. So we can see that our Fourier transform is built up of just direct delta functions, and we previously established that they were peaks of 0 width, and we normalized them so they were magnitude of 1. So we can simply draw our magnitude spectrums, and they obviously transform in the omega in the frequency by the inside of the brackets. So our first one is 3 pi times these two. So that will be one direct delta at 50 radians per second and the other at negative 50 radians per second. And just draw them in as straight lines. And this will be our magnitude spectrum. Our magnitude here will be 3 pi. And then on the other side, we have the same thing. We can ignore the j because we know that we're using magnitude, and we can just take 2 pi times these two direct deltas, which are at 150 radians and negative 150 radians. We can draw them out like this. Is everybody comfortable with drawing these direct deltas? It's pretty simple, you're just drawing straight lines. And then in terms of our phase, this might be slightly more confusing. We have to look at the real and imaginary components of our Fourier expansion or Fourier transform. If we look at the 50 and negative 50 hertz peaks, we can see that they are both real. And so real signals have 0 phase. So we can simply put them in as 0. In terms of the next two, we can see that they have a j term, so they're imaginary, and they will have phase. Multiplying by j rotates our signal by 90 degrees, multiplying by negative j rotates it by negative 90 degrees. So in this case, we have positive j for the direct delta at 150 radians, and a negative j at the negative 150. And so that's at 90 degrees and negative 90 degrees. And that is all you have to do for sketching the spectrums of this Fourier transform. Is everybody clear on how I drew these, or do you want extra clarification? Yep, we're all good. For question D, we're asking you to consider another RC circuit. Let's write down the values that were given to start off with. Okay, we aren't given any values. It's a justification question. So at frequency omega equals 0, will the amplitude of V0t be larger, smaller, or equal to the amplitude of the Vi of t? Then we have to justify our answer. So the first thing to note is we're using omega 0, and at DC, our capacitors appear open. So we can immediately simplify our circuit to 2 resistors. And we are looking for the amplitude of V0, so plus minus V0. Specify using voltage division. And I think that is it. It asks us to explain by how much, so what factor, and that's simply taking the inverse and saying B0 is R1 plus R2 on R2 times smaller. In terms of justification, I think it's as simple as saying that at 0 frequency, the capacitor is open, and we can show that ZC equals 1 on 0C, which is infinity, an open circuit. If they want lots of detail, they do ask for a detailed answer, but I think it's quite a simple question. For the second one, they ask for the frequency 2 pi and t, and the same question whether it would be smaller or larger. We can use the same method that we've been doing in previous parts of this exam. We can add the capacitance or the impedance and the resistance in parallel and voltage division again. So and then using voltage division again. I'm always right what technique I'm using, so the amount of nodes. I'll simplify first to be a fraction. Again, multiplying through top and bottom by J omega C. Exact same steps. We get our V0 in terms of VI. In this case, we are given a frequency of 2 pi on t. Substituting that in. Well, I guess first we should take the magnitude of transfer function here. So we want the amplitude. And then if we say solve that, maybe it's 2 pi t. Substituting omega in is simply this long and tedious equation. And then in the same way, we can say that VI will be smaller than V out will be smaller than V in using this transfer function. We can clearly see that this will be larger than the numerator will be smaller than the denominator. I'm just saying it's so simple. I'm not going to write that again. On that. Smaller. Is everybody clear with these questions? I think the key thing here will be the justification. So we need to justify that the capacitor will up here open. And we need to justify here that R2 is smaller than this denominator. Okay, I'll move on to what looks like the final question. And yeah, we still have 20 minutes. So at the end, I guess if anybody has any questions they want to bring to me or specific examples they want solved, I'd be happy to do that. So for this question, we're asked to prove the maximum average power transfer. You could look at lecture notes to solve this, but we're just going to go through this, see if we can do it, derive it for ourselves from memory. So again, we're using voltage division a lot. We're going to use it again. Oh no, we're just going to use. Yes, we're going to use the fact that I squared times the impedance will equal the power through the load. And obviously, when I say I squared, I mean the RMS voltage that needs to be taken into account in an AC signal. So we will start by finding I squared, the current. This is just Ohm's law, but the important thing to note is we can break up these impedances into the resistance and reactance. Then we want to find the magnitude of this current because we're going to be using the average power formula. So, and we'll square it. Yeah, we can then use this value in our average power theorem. Does everybody know why we're using RL here instead of the impedance ZL? So again, we can relate that back to the power triangle, looking at the real and the imaginary parts. The average power is the real part of the power triangle and the reactive power is the imaginary part. So if we just use the real part of our load, ZL, the imaginary part will be all in terms of the reactance, so XL. So in this case, we use RL and not ZL. Okay, so that is. So what's the first thing we can do to start maximizing this average power function? We want to minimize the denominator because RL always has to be positive. And the first thing I can see to do is to cancel out these two reactances. We can't cancel out the resistances because they are always positive, but we can choose. So we can choose XE equals negative XL. And those two will cancel out and we'll overall get a larger average power. From here, we can use the gradient and find the point where the derivative is 0. So say that dp dt equals. Oh, sorry, we're deriving in terms of our load because that's what we're changing. And so here we are using the quotient rule. So that is simplify that down. Let's cancel. Negative. And we can see that RC equals RL. Again, noting that resistances can't be negative, so we only take the positive solutions. So using these two things, we can say, therefore, maximize P average Z. Oh yeah, I see. And that is the proof for our theorem. Did anybody have any questions deriving that one? Question more about making sure you were paying attention in lectures and you have the mathematical facilities to solve it. Yeah, that goes. That's it for our questions. Does anybody have a specific problem they wanted me to solve or something they wanted me to go over again? Everybody's happy. Everybody thinks they're going to ace the midterm. I think you will. I'm confident. Okay, if nobody else wants anything solved, any questions answered, we can wrap up here.
Yeah, so thanks a lot, Felix. To those of you like in the room and online, we'll post the recording of this on our YouTube channel, the Elsoc YouTube channel, and we'll try to get it done soon. So yeah, thanks a lot, Felix.
No
That's
problem.
great.
My pleasure. Online has a question. Can we upload the solutions to this exam? Yeah, I can upload my solutions. Cool, sure, that's fine.
All right, I will stop recording and end the call. Thank you everyone for coming.